All right, so let's do some examples. If a coin has a 51% chance of coming up, 51% chance of coming up heads is flipped 10,000 times. Find the probability that at least half the coin flips were tails. So you look at this and you say, okay, we have a 51% chance of coming up heads. I don't think that that's necessarily an unlikely thing for a coin. When you're talking about a coin, we think of them as being fair, exactly 50% heads, 50% tails. But, the writing on one side versus the writing on the other side, it might be heavier. There might be minuscule differences that might be able to sway the probability of coming up heads versus coming up tails just enough to modify it. I don't know if 51% might be a bit excessive, but let's say this is really close to being a fair coin. But when we flip it 10,000 times, well, if we're flipping this coin 10,000 times, first we're going to find the probability that at least half the coin flips were tails. I'm going to first do this finding the exact value using binomial CDF. So let's think about what's going on here. We have 10,000 coin flips, so our trials, our individual trials here. Each trial, or each coin flip is a trial. So n would be 10,000. We're flipping the coin 10,000 times. The probability of a success, so I'm going to define what a success is here. In this case, we're counting the number of tails. So let's go ahead and say success is coming up tails. So the probability of a success, well, it's 51% chance of coming up heads. So that means a 49% chance of coming up tails. Remember, you do have to pay attention to what your success is. I was counting the number of tails, and I gave you the probability of the number of heads, or the probability of a heads. So you do need to be careful about that. Let's see. And we're saying the probability that at least half the flips were tails. So the probability that x is greater than or equal to, this is 10,000, half of them would be 5,000. So the probability that at least half the coin flips are heads, or tails, yes. At least half the coin flips are tails, is x is greater than or equal to 5,000. So when we think about this, we're starting off, technically we could go anywhere from 0 up to 10,000 heads, tails, keep going back and forth. We could go anywhere from 0 to 10,000 tails. We're actually interested in what's going on right in the middle, so let me just draw a couple of those in here. 4999. Okay, so if we're actually after 5,000 or greater, because I said at least that many tails, well, the binomial CDF gives us the probability of some number to the left. So to find this probability, to find the exact value here, what I'd want to do is I want to figure out the probability of this one and use my complement rule to find the probability of this stuff to the right. So I'm going to say 1 minus, that's my complement rule here. I'll do binomial CDF, because I want the CDF because I want this number or fewer. And then I'll just go ahead and say what my n is, what my p is, and what my x is. In this case, 4,999. Because I want it, my complementary event is the probability of getting at most 4,999 tails. So let's go ahead and plug that into the calculator. 1 minus binomial PDF, or CDF, 10,000, 0.49, 4,999. Takes it a little while because it's actually having to churn through that. So the probability here is 0.023, 233. Let's round to 4 decimal places. So the probability that you get at least half the coin flips being tails is just over 2%. That's actually really quite unlikely. Even though the probability is just slightly skewed towards coming up heads, the probability of getting at least half the coin flips being tails, you can see really drops off when we start flipping it that many times. All right, so this is the exact number. This is the exact value for that probability. Let's go ahead and use the normal approximation to find the value now, though. So to use the normal approximation, first off we have to have a binomial distribution, which we obviously do. That's what we just did. We need to figure out what our n and our p are. Okay, we have those. Then we need to use those to figure out what our mean is. So our mean is equal to n times p, which is 5,000. No, that's not 5,000. Our mean is 0.49 times 10,000, which gives us 4,900. Already you can kind of see why this value right here is pretty unlikely. Our expected number of heads is 4,900. We're talking about getting getting at least 100 more heads than our expected value. That's kind of why this is a bit unlikely. All right, so in any case, we also need our standard deviation, which we find by taking the square root of n times p times 1 minus p. I'm going to approximate this. So the square root of n, which is 10,000, times p, which is 0.49, times n minus p, or 1 minus p rather, which is 0.51. So this is the probability of it coming up heads. That's the probability, or tails. This is the probability of it coming up heads. So we get 49.98 and then a bunch of nines. 49.98999. Kind of no matter where I round this, you can see it's going to, well, actually I guess if I go 4 nines, it looks like it rounds off there. I think this is probably alternating between the 8s and the 9s, but yeah, whatever, I'll do that, because that's what it showed on my calculator, so why not? Okay, so we have our mean and we have our standard deviation, which means we can kind of think about what our normal distribution looks like. Our mean is right in the center, and we get, this is at 4,900. Our standard deviation is 49.9 whatever, so it's approximately 50. I'll just call this 4950 and 5,000. Over here is 4850 and 4,800. That's approximately 2 standard deviations to the left, 2 standard deviations to the right. Again, this is just kind of giving us an idea of what it looks like. We're actually trying to find the probability that we are at least half the coin flips were tails. That's going to be from over here. This is 2 standard deviations above the mean. We're going to go from here and to the right. Almost. We're not going to be going from 5,000 over. What we actually do is, remember when I was introducing this the first with the n equals 15 coin flips, you end up having to come slightly over. We went from 6.5 to 7.5. That's how we found the probability of getting exactly 7 heads. My drawing was pretty bad here. It's supposed to look something like that. So in any case, bumping over slightly. So not from 5,000 heads over, but rather from 4,999.5 tails. There I go again. I keep saying heads instead of tails. 4,999.5 tails or more. So going from there, 4,999.5 to the right, which that's something we can do using the binomial CDF, or the normal CDF. Normal CDF, or we'll do our left bound. Our left bound is 4,999.5. Our right bound is infinity. I'll just go ahead and call this 10 to the 100th. No, that's probably too big. 10 to the 99th? Yeah, sure, 10 to the 99th. I think that'll, whatever. That's pretty big anyway. It's a bit bigger than we need. Then we'll do our mean. Our mean, which we found right here, is 4,900. And our standard deviation, which we found to be 49.99. I'll just go ahead and round that, whatever. We'll ask our calculator what this is. normal CDF, we're going to go from 4999.5 all the way up to 10 to the 99th, 4900, and 49.99. This is approximately 0.02327. I guess if I rounded that to 4 decimal places like I did the first one, you can see we get 0.0233 compared to the 0.0233. That looks like a pretty good estimate to me.